everyone, my name's Merlin Chan and I'm going to teach you today a lesson in Calculus BC. Hi, I'm with my friend Pablo. He's so polite. Gee, interrupting me. Shh. Okay, here my friend Pablo, he's a man of wisdom, so he claims.
I do, what do you mean? I know everything!
Yeah, that beard isn't doing much for you. Okay, so today I'm going to teach you about power series.
Wait, what? What power series?
Exactly. That's what you're going to learn today. So, in order for me to teach you power series, I'm going to divide the lesson into 4 parts, and I'm going to go over the 4 parts right now with you.
You changed your shirt?
Dude, it's Florida. I was wearing a long sleeve. Come on. Besides, you're getting off topic. Well, my friend, you'll be fully prepped with knowledge once this video ends. Alright, so for a lesson on power series, there are 4 objectives that we're going to go through. And the first one is we're going to learn how to understand the definition of a power series. The second one, we're going to find the radius and interval of convergence of a power series. The third, we will determine the endpoint convergence of a power series. And the fourth and last one, we would differentiate and integrate a power series. Okay, so we're going to start by understanding the definition of a power series. The power series are the most important types of series, and they're the ones that the AP exam concentrates on the most. Okay, first we're going to see the definition of a power series. This one. It's a little different here because it has a different concept where x is a constant instead of a variable. And as you can see, we're starting from n equals 0 to infinity rather than from n equals 1 to infinity. This is because the first term is our constant. Alright, so the definition of a power series is a summation from n equals 0 to infinity of a sub n times x to the n equals a sub 0 plus a sub 1 times x plus a sub 2 times x squared plus a sub 3 x to the third, and then so on. Alright, so the next definition that we'll learn is the definition of a power series centered at C. It goes from 0 to infinity, the same as the last one, and it's a sub 1 times x minus c to the n power equals a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared, and so on, and you continue with the same thing. As your n increases, you plug it in. Alright, so if you guys are a little confuzzled about this whole centered at C thing, it's pretty simple, and I think it's the most easiest thing about power series. Alright, so we have this series of summation of from n equals 0 to infinity of x to the nth over n plus 1. And what we simply do is that we get this, the x, and we set it equal to 0. Alright, so this is a simple one, x equals 0. So we conclude that this power series is centered at c equals 0. Alright, so we're going to the next one. Shh, don't look at that. Alright, so example number two says that we have our series here, summation of n equals 0 to infinity of negative 1 to the n times x minus 3 everything to the nth power. Alright, so again what we do is that we get this and set it equal to 0. So we get x minus 3 equals 0, and then we get x equals 3. So we conclude that this power series is centered at c equals 3. Alright, so our next step is to find the radius and interval of convergence of a power series. Alright, so a power series in x can be viewed as a function of x, where the domain of f is where the power series converges. The main key is to determine those domains. Alright, so for a power series centered at C, precisely one of the following is true. You have 3 options. It's either the series converges only at C, or there exists a real number r is greater than 0 such that the series converges absolutely for the absolute value of x minus c is less than r, In other words, for some open interval negative r to positive r, or it will diverge for x minus c, the absolute value of that greater than r. Or number 3, the third option is the third option is for the series to converge absolutely for all x. So, in other words, from negative infinity to positive infinity. Another thing that we have to keep in mind is that C always lies in the domain of F. Right, so, to prove that C always lies in the domain of F, we can see that the domain of a power series has only 3 basic forms. A single point, where the only point is C, which is that the series only converges at C. An interval from R to negative R. It doesn't have to be negative, it's just the left side of that. Or, and that includes this whole thing, right? That's where the series will converge. Or the third one is that the series converges in the entire real line. So the whole entire line. Right? We're going to go into an example of how to find the radius of convergence for a series. And then we're given the summation is from, from 0 to infinity of 4x to the n over n squared. Alright, so first what we do is that when we're trying to find the radius of convergence, first we apply the ratio test to our series. And if you guys don't recall the ratio test, you just take the limit as n approaches infinity of your series. And what you do for every n is that you just add 1. And then you multiply it by the inverse of the series. So here we have 4x to the n plus 1 power over n plus 1 squared times this flipped, which is n squared over 4x to the n power. Alright, now we're going to simplify. And here what we did is that and the 4x to the n's crossed out, so we're left with 4x, and then we multiply and we get n squared over n plus 1 squared times 4 to the x. Right now we find the limit of this, and then what we can do is we can take out the 4x, put it here, act like it's not there, and once we take since it's a constant and n is our variable, it doesn't really apply, like it's not necessary for this. So now what we get, since the limit of this is 1, because they're the same degree, they have the same degree, it's 4x, which is our constant, times 1, which is the limit as n approaches infinity of this function. And then what we do is that we have to find where r is less than 1, right? So we have 4 times the absolute value of x less than 1. Then we solve for x, and then we get r equals 1/4. Alright. Okay, now the third part to our lesson is how to determine the endpoint convergence of a power series. Okay, we don't know much about the endpoints of the interval of convergence. We know the series converges for all the values within the interval, but we now have to test each endpoint individually for convergence or divergence. And that's what we're going to do next. Alright, now so we're given a series, and it's right here, the summation of from 1 to infinity of n over n plus 1 times negative 2x to the n minus 1 power. So like we did previously, we apply the ratio test to this series, and we have the limit of, as n approaches infinity, of the equation of, we add 1 to every n. So here we have n plus 1 times negative 2x to the n, and it's n minus 1 plus 1 is n plus 0, which is right here, over n plus 2. And then the the reciprocal of what we're given here. So that's it. Here, next, what we do is that we cross things out, right? So here, the negative 2x to the n crosses out with this one, and we're left with the negative 2x to the negative 1 in the denominator, but that's the same as negative 2x to the negative 2x in the numerator. So we keep it right here. And then this times this is n plus 1 squared, and the bottom is n times n plus 2. So once we take the limit of this, like taking this out here, like it's not there because it's a constant. The limit of that is 1 because it's the same degree, the top and the bottom. So we are left with 2x. Our r becomes our 1/2. So now, since it's the absolute value, we have the interval. Our interval is from negative 1/2 to 1/2. And now what we do is we want to test the endpoints, right? So we're going to test negative 1/2 first. X equals negative 1/2. And then we plug it into here. We get negative 2x times negative 1/2 is positive 1. To the n minus 1 power is just 1. So we're left with the summation from n equals 1 to infinity of n over n plus 1. And we can use the nth term test. Sorry, nth term test. And we're left with, since once we take the limit of that, since it's the same degree, it's 1. So 1 is not 0. So the series diverges. And now we test x equals 1/2. And then once we plug it in, negative 2x times positive 1/2 is negative 1 to the n minus 1 power times n plus 1. And this is an alternating series. So there's 2 tests to the alternating series, and this doesn't pass the first one, which is taking the limit of that, which is also 1, which is not 0. It's not equal to 0. So by the alternating series test, this series diverges. So now, since we have tested both endpoints and they both diverge, meaning they are both not included. Oops, where are you going? So our interval, it's just negative 1/2 not included to 1/2 not included. And that's how we find our endpoints. The next section that we will be covering is differentiating and integrating a power series. Function for a power series here, and then to derive it, we simply carry the n to the front and then subtract 1 to the exponent. In other words, we integrate. We simply add 1 to the exponent, and then we carry we multiply the function by the reciprocal of the exponent, which in this case we're dividing by n plus 1. Now we're going to find the interval of convergence of f of x, f prime of x, and integral of f of x. And for the first one, we apply the same process, and we get that f of x converges from negative 3 to 3, both non-inclusive. And now we take the derivative of this function. We end up with this, and we apply the same process, and we find that they have the same convergence as f of x. Next, we're going to integrate, and we start by integrating f of x. We end up with 3 over n plus 1 times x to the third, x over 3 to the n plus 1. And then we do the same process, and we find this process being different in the way that once we plug in the endpoint negative 3, we figure out it actually converges instead of diverges, which that's what's been happening for the previous problems. And proves what we saw earlier, that once we differentiate and integrate, the radius of convergence is the same, but the interval of convergence may differ for certain problems. At the